what you transmit. Let's say you concentrate the power here, so this is PT is how much power you're paid for, so this is in watt. This is a pulse. It has no dimension, so this G of t for me is some pulse whose peak is 1. So it is unitless. And then you have the modulation. And what you receive after demodulation is as receive of t, the received power, so how much power you get back from the target. The pulse is delay according to twice the distance divided by the speed of light, and then you have the phase, which is minus j, let's say 4 pi divided by the wavelength times r. I am assuming, of course, a monostatic system. Meaning that this is my radar, this is my target, the waves goes to the target and gets back to the radar, and this is the distance. Last time we wrote that this is the signal after demodulation, because you see that here you have the a fast varying sinusoid which has disappeared here, because this is after demodulation. But since from now on I will only consider this signal, we can just skip this term, and it should be clear based on the context. So this is after demodulation. So this term, this received power, we say that it is this is something that you get from the radar equation, and so this is your transmitted power divided by the spherical divergence term square, because it is two-way, so the wave goes to the target and comes back to the radar, times the gain, times the area of your antenna, times the directional function, so the antenna pattern squared, because it is two-way, times the radar cross-section. And this is your information about the target. Of course, if you have we say that if you have multiple targets, then this becomes a sum. So you have SR of T. This is the sum over all the targets. The square root of the power received from each target. This is the pulse with the delay from each target, and the phase of each target. And so, of course, as long as the targets are so as long as the distance between two targets differs by more than your range resolution, which is half the speed of light by the pulse length, then you are able to see two peaks, or say many peaks, as many peaks as the number of targets that you have. So you are in this equation. So I don't know, the first peak is a motorcycle, the second peak is bigger, so it is a truck, and the third peak is a bicycle, whatever you like. But he said you may be in the situation where multiple targets contribute, let's say, where the peaks for multiple targets happen in the same resolution cell, so they do overlap in time. In which case, you have a complex summation among different targets, so they add up coherently, and this is a mess because you can have coherent summations or cancellation depending on the relative phase. So depending on this term here, they can sum in phase or cancel out each other. Now, this concept is this condition under which two targets are interfering with each other or not. So the condition by which they are they can be solved or not in distances is closely connected to the concept of resolution cell. So the resolution cell is the portion of space which corresponds to a single sample in your data. So if you have an image, it's a pixel. So what does this pixel correspond to? If you have a time signal, then it is just a time sample. So what does temporal instant correspond to? In our case, so we are not considering images yet. We are just looking at 1D signal. So resolution cell means that, for example, this is t. This is a particular time instant, so let's say t sine. And the resolution cell corresponds in the 3D space to the region of space which is at the same distance from the radar. So for example, now in 3D, just imagine two concentric spheres. This is 1 and this is 2. This spacing between these two spheres is exactly one range resolution interval. So this is delta r, the speed of light by the pulse length. And so your resolution cell is this portion of space. Meaning that all the targets within these two concentric spheres will collapse in this point. Of course, if you also consider that your antenna has an orientation as a beam, now this spacing is not the whole solid angle, but most likely something like this. So your resolution space is actually this one, and you do not consider these other parts. But let's say the spherical sector between two concentric spheres. If you take a look at the section, so for example, this is, imagine that you have a radar like an airborne radar, which is flying orthogonally to the blackboard in your direction. So this is an airborne system which is carrying a radar, more or less. Assuming that we are looking slanted, so this is the portion of space that we are illuminating. I can put some numbers here. For a typical airborne experiment, the antenna pattern changes from like 15 degrees to some 60, let's say 15 to 60 degrees, more or less. So depending on how high you're flying, then you are illuminating a certain portion of the ground. Now your resolution space, your resolution cell in this plane corresponds to a fixed range, meaning that all the targets that fall into this region of space will collapse into a single point here. So for example, you have here, I don't know, this is the terrain, then you have a tree here, I don't know, you have a house. And so in this resolution cell, you have the terrain, part of the crown of this tree, and part of the roof of this house. Okay? These three targets will end up here. So you cannot resolve them because they fall in the same resolution cell. As simple as that. So now, let's characterize this a bit further. So let's assume that all the targets in the same resolution cell are also seen from similar angles, because we have a beam, so we are looking more or less at the same angles. And so this means that, okay, this term is common to all the targets in here. The gain and the area of the antenna at reception are of course the same for each target in here. This the antenna diagram is slightly different because these targets are seen under slightly different angle, but if they are sufficiently close to one another, then we can assume that this is again a common term. The distance is of course a bit different, but it can only differ for one target or another by a fraction of your range resolution. So if we assume that your range resolution is not too coarse, so let's say range resolution on the order of a few meters or something, then we can also assume that this term is constant. So we can bring all of these terms outside this summation here. Of course, the radar cross-section depends on the target. And so here, for example, one would expect that the radar cross-section for the, I don't know, for the tree crown is larger than the radar cross-section from the terrain, for example. And so in the case where one of these targets has a much stronger radar cross-section than the other one, this is the dominating term. But what is fun is when all the targets in the same resolution cell have more or less the same radar cross-section. So let's assume that maybe in this case you are just looking at the terrain, and in your resolution cell you have many scatters. I don't know, you're looking at a gravel terrain, and so you have like gravel stones. And so each little stone is contributing as a target for your radar. And so your signal is contributed by many different target distributed in this resolution set and with more or less the same radar cross section. Okay, this is interesting because in this case it means that you can write this signal more or less in this way. Oops, sorry. So I took the term that tells us about the backscatter power out of this summation under the hypothesis that you have more or less the same, that the targets are similar to one another. And then I wrote here G of 0. Why? Is that clear or this is a mystery? Of course, I am, or maybe I should write it this way. T in T signed. So I am evaluating the signal here. So at a precise time interval, or let's say at I am evaluating only the time instant for which t is equal to 2 divided by the, let's say, the average distance of all the targets. If you like, I am evaluating the signal at this point here. This is very simple for me, but maybe it is not. Is that okay? So I am okay. So in this case, we say that the peak of this pose G is 1, and so I can forget about this term. So I get this signal, which is contributed by all of this term. We say that this phase, so this phase changes very, very rapidly. So for example, when the distance of the target to the sensor changes by half a wavelength, then this phase changes by 2 pi. And so even very small variations of distance result in very large phase variation. So this means that, for example, if this resolution cell is, I don't know, 2 meters or 1 meter, your wavelength is 5 centimeters, then from this target to this other target, your phase is changing very, very rapidly. Changes by, so we say 1 meter, this is hundredth of radians in your resolution cell. So if you assume that your targets are more or less random, so there is a random distribution of your target inside this resolution cell, then this one can be considered as a random signal, meaning that this phase here, so let's call it phi, k, this phase here can assume all the values, all the possible values with the same probability. Yes?
But this is because we assume to have distribution of the targets that is totally random.
Let's say if you have a continuous distribution, then you will see a phase that changes by many radians in your resolution cell. So it is true that every phase value is possible. Now, if you assume to just take a bunch of cobblestones and spray them onto the ground, then you will get more or less that every possible phase that every phase is equally possible. Of course, this is true as long as your resolution cell is much larger than the wavelength. If this is not true, then this game that even a small distance variation gives you a huge phase variation is no longer true. And in this case, it changes. This would be a game changer. But we are under this hypothesis. And which, by the way, means that your central frequency is much larger than your bandwidth. So let's say that if this is true, if you have a factor of 2 or 3, then your phase is random. Now, if your phase is random, then we can write that so let's say that this is a random variable uniformly spaced between plus and minus pi. And we are assuming that you have a lot of this target in your resolution cell. So your signal is also a random variable. And so it makes sense to characterize it in a probabilistic way. And so, for example, what do you think is the distribution of your signal here? Gaussian. Why?
Because I have a sum of random variable.
Okay.
So for the central limit theorem.
Perfect. So the keyword here is the central limit theorem. Which says that if you have a random variable which is obtained as the sum of a number of other random variables, independent, and this is surely the case because the position of each stone is independent on the other, then this variable tends to be distributed as a Gaussian variable. This is complex, and so your received signal at time t is a complex normal variable. C stands for circular, actually, meaning that the real and the imaginary part are evenly distributed and zero mean. I should have said zero mean because this was my next question. What do you think is the average, the expected value of this signal? I just told it, okay, 0. Why? Well, this is easy to do. You are the sum of a lot of phases, any of which is equally possible, and so they tend to cancel each other. And so the expected value of this signal is for sure 0. What about the variance?
Delta squared on 3.
Who's speaking? You? Okay.
It's uniform. As
What do you mean?
As we assume that it's Gaussian.
It's Gaussian, yes.
Okay.
For sure, its distribution is for sure Gaussian. So what do you think is the variance of this variable?
N square.
N square what?
Number of elements on the sum.
Okay, okay, this is correct. And why? Because, let's see. I want to compute the, so we say it is 0 mean. Because the phases do cancel out each other. And so the expected value of S square, okay, the short version is all of these random variables here, so these phi k are independent and 0 mean. And so the variance, well, the variance of these, so the expected value of a single random variable, this is for sure 1, because the squared magnitude of a complex exponential is 1. Since they are independent, then you get that the variance of the sum of a number in the independent variables is the sum of the variances of these variables. And so this is n. Let's say it is these terms squared multiplied by n. PT so number of targets in my resolution set. If you want a longer version, then we are, so let's say that you have a variable v, which is the sum of these many complex exponential. So v absolute value, the squared absolute value of v is equal to the double sum for k and h. No? And this is something that you can write as the sum of the terms with the same index. So which is 1, plus the sum of the terms with the different indexes. We say that any two phases are independent on each other, and so the expected value of this term, so if you take expectation, then you have the expectation of this term here is equal to the product of the two expectation, which we just say that it is 0. So 0 times 0. And you only have this term. So n times 1 is n. So you have a complex signal. Okay, this is okay. I will not write it again. This is the variance of this complex number. How do we characterize it? So you can say that in average, because this is the expected power, but of course if you take the squared magnitude of the signal, then you have oscillations. Maybe you also remember that for a so for a complex Gaussian variable, so let's say that PS is square magnitude of S received. So PS is another random variable. Of course, the expected value of PS is this one. And so in average, this is the power of your signal. You have also power oscillation, and the variance of your power oscillation is something that you can compute easily, because this is a Gaussian variable, and this is equal to the power to the second. Okay, you remember this, okay. Oh, you trust me. Yeah. Okay, so this means that your signal is random. You can as well get a 0, even if you have target. If you get a 0, you also get 0 power, because 0 squared is 0. And so when you evaluate the power, you again have oscillations, and this is the variance of the power. So if you like, the square root, so the standard deviation of your measurement of power is equal to the expected value of your power. Oops, sorry. I should have wrote here expected value, of course. So you get something that is oscillating, and this is unknown, of course. Huh? And this is what you have when you have many targets in the same resolution set. Oh, and sorry, very importantly, how do you characterize this case? Well, we say that this radar cross-section is a concept that was introduced to somehow decouple the expression of the power that gets back at you in a part which is due to your system. So the gain and the power and the distance, well, distance is geometry, and a part that is due to the target. So the idea is that this RCS is only due to the target, even though it is not exactly the case as we discussed. Now, we have this factor n, which is again due to the system. So n is the number of targets in the same resolution set, which means that this is my terrain with a lot of scatterers, this is my system. Now, if I send a very short pulse, then my resolution cell has this form, and so I only have few targets for each time instant in my received signal. If I send a very long pulse, then this is my resolution cell, and so I see many more targets. The same thing is also, so now try to rotate the board. So imagine that I am flying in this direction, and so I am illuminating a portion of space like this. So your resolution cell in display, maybe it's better if I were, so this is height, this is the ground range, and let's say that you find like this, so this is x, and now here this is x and this is y, and the height is coming to you. So if, for example, you have a very short antenna, then your pattern is very large, and then your resolution cell is huge. If you have a very long antenna, then your pattern is very short, and your resolution cell is smaller. So again, the number of targets in your resolution cell is also due to the system, which is annoying. We don't like this. And indeed, this term, RCS times n, is recast as a coefficient sigma 0, which is called the backscattering coefficient, times the area that you are illuminating. So in this case, this is your illuminated area. So this is something that you can predict if you know at least approximately the geometry of your experiment. So you know how high you fly, and so you know your antenna pattern, so you can more or less predict what is the extent of where the beam goes. And this is a coefficient. Say this is the backscattering coefficient. Which is characteristic of the target, and then of course also of the frequency and of the particular incidence angle. So you have the same drawbacks as in the case of the radar cross-section for single targets, but you can at least use this to characterize a distributed target univocally. And what is interesting is that if you browse the web, you find this value for a lot of different targets and different frequencies. So, for example, if you assume that you are illuminating, I don't know, a grass field or soil and rocks or a vegetated area or the sea or sand, whatever you like, then you can have an idea about the reference value for this number. So we say that the RCS was measured in square meters. So the backscatter coefficient is, of course, this is equal to an RCS times the number of targets per square meters. And so your backscatter coefficient is unitless. you can also have the case of a volumetric target. So now I'm assuming here a surface target, which is for our application the typical case. But if you assume that you are, for example, receiving the signal from the rain, so this is your resolution cell, and you have many raindrops. Then for a single time instant, you get the signal from a small volume. And so in this case, well, it doesn't change anything here. The expression is again the radar cross-section of any single raindrop times the number of raindrops in your volume. When in this case, we define the volumetric backscattering coefficient, of course, as the RCS times the number of elements divided by the volume. So in this case, your volumetric backscattering coefficient is measured in meters to the -1 inverse meters. So I have an exercise to show you, but I prefer to go ahead with the theory and then treat it all together. Okay. So far, what you know how to do so far is how to predict how much power you will get based on the information about the system geometry, based on the information about how your radar is done, and based on an information about the target. Okay, is it a single target with a fixed radar cross-section or a distributed target with some backscattering coefficient? What you cannot tell as yet is if this power is sufficient or not. We said last time we computed the power in a specific case and we saw that the return was very, very weak. So it was like 10 to the -12, I think. So, okay, 13 watts. So very, very low. The question is this enough? Are we just getting, so are we getting a useful signal, or we are just getting something that is too weak to be used? Well, it all depends on how much noise you have. So what we should include here is noise. And the question is, you are getting your signal back and you're also getting noise. So when we consider the signal, the received signal, then we should consider something of this kind. So your received signal, we say it's equal to the received power, your short pulse, plus the phase, times the phase, plus a noise. How should I call it? N. Noise of T. So what you get is your peak plus this noise. Now, you all gave communication, so I think that you already know how to characterize this noise. So for what concerns this course, this noise is again a circular Gaussian variable with zero mean and with variance equal to the KTB. So the Boltzmann constant by the temperature times the bandwidth of your antenna. Again, for when you consider the noise on your received signal, I think it's easy to also include the noise figure F. Let's write it this way, FB, which accounts for all the circuitry from the antenna to your final signal. So the noise figure here is accounting for the whole system. And so this is the power of your noise. You also know that you can counteract for this noise by filtering the signal. And I am sure that you know the concept of matched filter. Right? Okay, so what I do here is that I filter the signal with the replica of my pulse. And what I get here, so let's say that this is the signal, let's say after filtering, is the received power times I am filtering G by its replica, time reversed and complex conjugate, and so I get the autocorrelation of G in T minus 2R divided by C. The phase is the same, of course. And then you have the filter noise. So after your signal passes through a matched filter, then its expression changes a bit. This R of G is again a short pulse, but its peak is no longer one. Its peak is the energy of G. And this W is again a complex normal, a complex Gaussian variable, a circular Gaussian variable, zero mean, and whose power is KTF times the energy of G. So the signal to noise ratio, which is what counts to the aim of revealing the target, is the peak of the signal divided by the power of the noise, and this is PR times the energy of G squared times KTF. Oh, this of course is also called M0. you know it, times the energy of G. This one goes away, and you end up with the received power times the energy of your force G divided by M0. No magic, no? You're all writing, but you know these are. What is the unit of this one? Seconds. Okay, not easy. So since we did define G of t as a unitless signal, then its energy is measured in seconds. So this energy of G is representing the effective duration, the effective time duration of this force. And so this is, since this is a time, this is the received energy. So this is the energy that you are collecting from a target divided by the spectral density of a noise. This is standard communication theory. Now, what is very interesting here to the aim of designing a radar system is that what counts is the energy, not the power, it's energy. So, if you want, okay, this one, you just cannot change it. So, for example, if you're looking, so this depends on the both one constant, which is a constant from the noise figure of your system, which you cannot change it unless you modify your hardware, and from the noise temperature. So you cannot work on this one unless you're, well, you can, too complicated, sorry. Let's say that we do not want to modify this term here in this course. But we want to notice that since what counts is the energy, you have two choices. You can either send a very short peak with a very large peak power, or you can send a very long pulse with a very low power. So since what matters is just the product between the power and the time. Now, I am asking you, which of these two solutions do you like best?
The second one.
Why?
The chip.
The chip, okay. Who told you about the chip? Monty?
No, Prati first.
Okay, so you have a very nice reminiscence of previous courses, which is great. You of course prefer to send a very long signal, so a very long pulse. So this is T. Let's say that the absolute value of our signal is this one. And at a low transmitted power. Because in this way, let's say that you are not stressing your hardware. You are not requiring your hardware to send a big amount of power in a very short time. So you can just turn it off, on and off. And you just let the time do its work to give you energy. Okay? You know the answer, so do not answer into the next question. We are sending a very long pulse. Is this bad for the range resolution? Does this mean that we are losing resolution? We say that your range resolution is half the speed of light times the duration of the pulse, which now is very long. So, at least at the first glance, we are losing our capability to resolve two targets. Any comment on this? Not you, huh? No, not at all. Would you buy this system? This is the absolute value of the pulse we are transmitting. Very, very low. Let's say that this is I don't know, 1 kilometer. Would you buy a system with this pulse?
Depends on the application. It depends on the application.
You want to detect cars, so you need a resolution of the order of few meters. No clue? So I give you 100,000 euros. You have to buy a radar and you can keep the difference. This one costs 30,000. Would you buy it or not? But you have a strict requirement. You have to detect two different cars traveling close to one another. So you need a range resolution on the order of 1 or 2 meters. And I am offering you this radar. This is the magnitude of the pulse, of the transmitted pulse, for 30,000. Would you buy it? If you miss the requirement, then you have to pay a fee. So you have to pay 200 euros, 200,000 to your contractor.
Maybe I have to see the phase of the sea.
Ah, yes. What about the phase? The question is that this is not telling the whole story. What about the phase? Huh? So if the phase of the signal, so let's say that, oh, I lost it. Okay, we say that after you filter, this is ROG, and this is data. So what matters for your range resolution is the autocorrelation function of your pulse. It is not your pulse. Huh? So if this signal has an autocorrelation function which is maybe like this, then this is your effective, let's say, this is what matters for your range resolution. Huh? And how do you know about the autocorrelation function? The answer is phase, of course. It is due to the phase of the signal. You can, for example, notice that since the autocorrelation function is given by GT convolute, oops, G of T convoluted by itself, then its Fourier transform is equal to the squared magnitude of the Fourier transform of G. From polarity, you have to know it. And so, this means that your signal G of t has to be such that, so let's say, in the Fourier domain, then it is GDF, which has some magnitude and some phase. And this phase doesn't count, because it is always cancelled out when you do this after method filtering. So this is a degree of freedom that you have to ensure that your pulse is very long in the time domain when you transmit it, and then it shrinks, and then you can compress it to a very short pulse with this simple operation. Now, a particular solution, there are a lot of solutions to do that, but one particular solution which is very popular in the radars is to transmit a signal like this. So the chirp. This is called chirp. Its absolute value is this one, so it's G of t, and this can be very long. Its phase is a parabolic phase. And the Fourier transform is approximately something like this. It is a rectangle, a rectangular pulse whose bandwidth is equal to this alpha coefficient. This is called the chirp rate, times the total duration of your signal, and then its phase is parabolic again, so the phase is something like this. This is the absolute value of the Fourier transform, and this is the phase. Of course, the phase doesn't matter here, because when you do method filtering, it is just cancelled out, and you're left with this magnitude, which is more or less a rectangle with a very large bandwidth. Now, if in this case we say that this magnitude is more or less rectangular pulse with bandwidth equal to R times delta t. And so the autocorrelation function is approximately a cardinal sign, and the log width is 1 divided by b, and so 1 divided by alpha and delta t. So you get the chirp paradox. The longer the chirp is, the wider the bandwidth is. This is counterintuitive. Usually the longer is the signal in the time domain, the narrower its bandwidth is. So the chirp is a counterexample. The longer it is, the larger the bandwidth. And so your real range resolution we say that its duration is 1 over b. So your real range resolution is half the speed of light divided by the bandwidth. So your question to know if buying this 30K radar is a good deal for you should be, how large is the bandwidth? Because the bandwidth is what gives you range resolution. The math is clear, no? It's quite standard. Any questions? Okay, so just to give you some typical figures. So I put in your Dropbox folder a snapshot from Wikipedia, which is listing some characteristic transmitted power. So for example, 100 kilowatts is the typical transmission power of an FM radio station with a 50 kilometer range, and this is absolutely huge. I think that you kill little birds this way. No kidding. Now, for a typical spaceborne radar, the transmitter power is about 1 kilowatt and a half, so 1, 2 more or less, which is more or less the power that you need for ironing your shirt. So it is not bad. And 100 watts is the typical total thermal radiation by a human body. So I am emitting more or less like a fraction, but let's say a significant. Let's say that 15 men can substitute a spaceborne radar, more or less. And about 2 watts to 1 watt to less than 1 watt, let's say, or 100 of milliwatts is what you need to use your cell phone. It mostly depends on the technology. I think that cell phones in the 90s would emit like more than 1 watt. Now I think it's much less, but let's say 100 of milliwatts, more or less. And 1 watt is also, I would say, I saw airborne radars working with 1 watt. So more or less you can put your cell phone on an airborne system and end up with a decent image, a decent radar image of what you're looking at. And this is amazing. And the key to this is just to let this time be sufficiently long to collect energy. So even if you have a very low power, it is gonna work. Okay, now I Okay, the time, so time is running up, so I don't think I have time to show what I want to show. But I prepared, or well, no. To be fair, I recycled an exercise for you, so I cannot lie and tell you that I've prepared expressly for you because it is commented in Italian, so my apologies to foreign students. I promise I'm gonna translate it in a very few days, okay? And this is a MATLAB code that is more or less simulating an airborne experiment where you are transmitting, calculating how much power gets back at you. Then you will be simulating the presence of a few point targets, so a few single targets. Do this operation, so you transmit with a certain chirper, you do this method filtering, you end up with, you see, I just cancel it. So you see this pulse compression thing. You also add noise and you measure the signal to noise ratio with your PC and check that it is as you expect based on the theory. So just give me 1 second to install the projector. Then turn off the light. So here your Dropbox folder, where is the radar imaging? So you have a subfolder now, MATLAB code. Okay. And you have this radar aerial, so airborne radar. So, can you read it? Is that okay? Okay, so these are the data of your problems. This is your central frequency. This is the speed of light. This is the backscatter coefficient. In this case, this is typical for soil and rocks. So for this kind of terrain, you have a backscattering coefficient of some -15 dB. so it's 10 to the minus 1.5. This is your flight height. So I am imagining exactly this. I am imagining exactly this geometry. So I'm flying as before in your direction. This is 4,000 meters, and I am looking at the side of my aircraft. So I am emitting in this angular sector. I am imagining that I have here soil and rocks, and so I am getting the signal back from all of these points. If you rotate this, then this is the flight direction, X. This is again Y and Y. And I am also considering the azimuth pattern of your antenna. And so for each time instant, your range resolution cell is this one. So the targets that will contribute to a single time instant are all the ones in on this segment here in this plane, and of course all the ones in this sector in this other plane. So more or less like this. So with this in mind, here you have some information about the azimuth aperture. So this d phi is your azimuth aperture, d theta is your elevation aperture. So this is d theta and this is d phi. Theta 0 is the pointing angle, so it is the center of the beam, and this is your bandwidth. So the first part of this code is just computing for you how much power you get back. And so here I'm just computing the range resolution, you see, and I compute this based on the bandwidth. I don't even need to know how long is the pulse at this stage. This is just the minimum and maximum range and the area of your antenna. And this is just the radar equation. So I am just implementing here the radar equation. This is this area Versailles is the area of your target, so the illuminated area. This is exactly this area here, which sheer geometrical analysis you get that this is equal to your range resolution times your azimuth aperture times the range. And this is the radar equation, nothing more than that. And you see that I am computing the total radar cross-section as the product between the backscattering coefficient and the illuminated area. So exactly what we just said, and this is a graph. And this is your power. It is plotted against range, so against the distance from the radar. This is your range. This is R. And so you see that it is initially going up. Why is it going up and then down? Can you predict this trend? The geometry is this one. I have an antenna pointed like this, so it is pointed at 40 degrees, and this is just the power that you get from, let's say, from any point on this table. So the range, so the shortest range is this point here, and the farthest range is the end of the desktop. Why is the power going this way?
Distance.
So it goes down because of the distance. Yes. Why does it go up in the first part of the plot?
He's pointing in the
Exactly.
maximum of the.
Exactly. Antenna pattern. So, okay. So this is already the combination of your antenna pattern and the range. And so this is what you get. It is like minus 445 dB. It's really very low. Now you get the power. This is the evaluation of the signal to noise ratio after matched filtering. These two elements, I will comment on these two parameters the next time. This is your total observation time. So this is the length of the signal you are transmitting. Okay, and so the energy of your signal is simply obtained as the power times the total observation time, as we just said. This is the noise, so the Boltzmann constant. The noise temperature, I am just assuming 290 kelvins, because this is the standard noise temperature if you're looking at the Earth surface, just a reference value. Noise figure 4, again, just a reference value. And this is your signal to noise ratio. After matched filtering. So it goes to 10, then 15, 16, and goes down to less than 5 at the end. But it's not bad. Huh? It's always larger than 0. So you always, even if this power is so low, you always get more power than noise, which is very important. And in this region, so your signal to noise ratio is better than 15 dB. So this is a very favorable signal to noise ratio. So in telecommunication, I know that you can get a nice, so you can extract information with a very low bit error rate, even at the signal to noise ratio on the order of 0 dB, or maybe even lesser, but that is because they have code. So in this case, we are just looking at the nature, and so we cannot use redundancy codes. Okay, maybe we can do something, but I don't want to discuss this now. And so more or less, assuming a signal to noise ratio on the order of 5, 10, 15 dB gives you nice performances. So if you want to study a target, having the signal to noise ratio is, at least at the very first glance, a good figure. Then this is my transmitted chirp. So this alpha is the chirp rate, And then I also want to simulate this chirp, so I have to set up the interval, the time interval where I want to sample the signal, and of course to fulfill the sampling theorem, I get the time spacing better than the inverse of the total bandwidth. This is the total number of time interval, and this is my chirp. So this G is your chirp. This is the Fourier transform of the chirp, and this is the frequency axis. There you go. This is the Fourier transform of your transmitted chirp. So it's a 100 megahertz signal, and this is its phase. We say that the phase is parabolic, and so you see it going very fast from plus to minus pi, because it is just going fast. But if you unwrap this, then you will see a parabola, and this is matched filtering. You see, I am convolving the transmitted pulse by its replica flipped, so reversing time and complex conjugate. Okay, I can just launch it here. So this one we saw it, this one we saw it. This is the transmitted signal in time. So this is a very long signal. This is its autocorrelation, so that it narrows down a lot. And indeed, this matched filtering is called in the radar jargon pulse compression, because you send a very large pulse and then you compress it a lot. This is okay. This is just this is not important. And this is the simulation. So you have here. I am assuming that I have 3 targets, so they are interfering with each other, and so the absolute value of the received signal is no longer 1, because the relative phase between these targets creates interferences, so you have summation and cancellation. This is when you compress the signal. You see here a single peak, but if you zoom in, 1, 2, 3 peaks that represent your 3 targets. And this is finally the same experiment plus noise. Your received signal is completely covered by noise. You wouldn't say there is a useful signal here. When you do range compression, pop, it just pops up, and here again your 1, 2, 3 targets with some noise, of course. So it is not as clean as in the first experiment. You can distinguish these 3 targets, and also this code outputs for you the measured. So this is an experimental assessment of your signal to noise ratio. So I am just measuring the power of the signal by taking the peak of the target, so the 3 peaks of the signal, and I can measure the power of noise just by computing the variance of noise. This is what I measure, and this is my theoretical calculations based on the knowledge of the Roy Geometry, so they are very nice again. So, we say that we will meet the next time on Thursday the 8th.
Yes.
Is that correct? So there is no intermediate exam for this course, but I just ask you to study this code. It is important that it is clear because your next homework will be something of this kind. So should you have any kind of doubt, just ask. So see you in 10 days, guys.